Hello everyone, I'm Sylvain Perrin, and today I'm gonna talk about storm-driven wave impact loads and Scour at a beach SEAWALL. I first want to thank Thomas Ayur and Elodie Bailly for their contribution, and also ARTELIA for allowing me to present today. The beach wall that we studied was located in La Grande-Motte. It's a French town on the Mediterranean coastline, and the council wanted to replace the existing beach wall over a 400-meter distance for aesthetic reason. As part of the 7.4 million rehabilitation project of the seafront, which is 50-year-old. The existing wall is an inclined wall at a slope of 15 degrees, and it displays a regular pattern of small steps of 1 meter wide and 20 centimeter high. The existing wall, shown on the top figure, will be replaced by a new wall which had similar overall length of 8 meter and slope of 15 degrees. But it will be a smooth wall, and it will integrate a small coronal element at the top with a 0.5 meter diameter. Work started last year in September, and they are planned to finish in 2021. The beach is made of fine sand, and the foreshore is a gently sloping foreshore at an average slope of 0.5%. The study objective was to compare the wall performance in terms of wave overtopping and scour, and to achieve this goal we used lightweight sediment modeling. The second objective of the study was to provide estimate of wave loads to the designer of the new wall. For this, we equipped a wall with pressure sensors and a load cell and carried out physical modeling. The fixed seabed considered for the wave load study integrated the maximum scour deduced from the lightweight sediment model study in order to maximize the exposed other area of the new wall. For the scour and overtopping assessment, we simulated an historical storm dated of 1997, and which had severe impacts in the region. We phased the storm build-up in 3 in order to capture the increased shallow water effects at the front of the wall. This figure shows the evolution of the spectral significant wave height over the seabed. We expected broken wave at the front of the wall, but as you can see, breaking starts further away from the wall during the storm build-up. This figure shows the temporal evolution of the 50-year return period storm events that we simulated for the wave load assessment. This storm peaked at a spectral significant wave height of 3.1 meter. We carried out physical modeling at the Hydraulic Laboratory of ARTELIA in our 1.2 meter wide wave flume. The modeling was carried out considering a 1:18 Froude scale for hydrodynamics and geometric conditions. This figure shows some photos during leveling of the sediment bed. Lightweight physical modeling provides a great advantage of giving a full visual of the hydro-sedimentary processes at play during testing. However, they bear the main disadvantage of being really time-consuming and requiring lots of effort during the process. It's therefore required to plan each step very carefully beforehand. We did that using analytical calculations and SBH numerical models. This allowed us to set the dimensions of the testera in terms of the length and the depth, and also the sediment characteristics. During testing, we observed the type of break-in and the type of sediment transport. Break-in was of spring type, and waves would break further away from the wall. And we did witness some rare plunging waves in the case of double wave formation. Sediments were mostly suspended during transport in the water column. At the end of each storm phase test, we will survey the seabed in order to provide details of the seabed profile and the scour information at the front of the wall. And as you can see, from a top viewpoint, morphological aspects were quite similar for the existing and the new wall configuration. This figure shows the time evolution of scour during the storm buildup. And it was interesting to see that the maximum scour was found at the intermediate stage before reaching the storm peak. This is a green curve. The modeling demonstrated that the new wall will cause an excess of scour of about 50% compared to the existing condition. And this was thought to be imputable to the increased random velocities on the new wall. During testing, we will collect and measure water and sediment which overtop the wall. And we demonstrated that the new wall would have a positive effect on wave overtopping, as the mean wave overtopping discharge was decreased by a factor of 4. Because of space constraints, we were unable to measure the time evolution of wave overtopping during testing. Therefore, we calibrated a SWASH model which solves the nonlinear shallow water equations. The calibrated SWASH model estimated the mean wave overtopping discharge to 4.4 liters per second per linear meter, which was a really good match with the measured one. It gave us a full insight of the wave overtopping events during the storm growth. The maximum wave overtopping estimates was over 1000 liters per second per linear meter. The SWASH model also gave us setup evolution over the seabed profile. There was a really good match between the model, the numerical model, and the physical model away from the structures. However, closer to the structure, the numerical model estimates were larger than the measured ones, and this was thought to be due to larger surf bit in the numerical model. The second objective of the testing was to provide wave load estimates on the new wall. So we equipped the wall with pressure sensors and a load cell. The selection of these instruments was based on preliminary calculation of the pressures and the forces, and whether or not we will be in the impulsive regime. Even if these estimates are really approximate, they are essential to make sure that the measuring capacity of the instruments are in line with what you expect. This figure shows the accident plots of the pressures measured on high flatter portion of the wall. That's the left-hand side picture. On the right-hand side is the accident plot of the pressures measured in the crown wall. As you can see, the pressures measured in the crown wall are at least 50 times larger, which is significant. And when you look at the time evolution of the signal, we clearly identified that we were dealing with impulsive loads in the crown wall, with typical time duration of 0.1 or 0.2 seconds versus 3, 4, or 5 seconds on flatter portions of the wall. The top figure compares the horizontal force measured by the load cell, there's the blue curves, and the horizontal force calculated by integrating the pressures, except the pressures in the Grenoble. As you can see, the pressures in the Grenoble can contribute up to 50% in the total horizontal force, which is really significant given the small size of this element compared to the overall size of the structure. Measuring pressures in the impulsive regime on a physical model should be made knowing that there are strong scale effects that apply. We made a rough estimation that scale effect could reach up to 60% in our Froude estimates. However, because of uncertainty of this methodology, we stuck to our Froude estimates in our recommendation to the designer. The type of results that we will provide to the clients are time series of pressure and force measurements, or any statistical values that they will require, and also the number of impulsive impacts in the Grenoble, which reached up to 22% during the storm peak. We also built an EH2 numerical model which solves the Run's equation. It required very fine mesh resolution, up to 2 cm mesh size, to capture the curvature of the wall. The results were in the same range than roughly as the measured one. We did not investigate further, but this numerical model could have potentially been used to provide wave load estimates, however not in the impulsive regime, as this model is a monophasic. To conclude, physical modeling was able to account for the small geometrical differences between the tools, and therefore provide a detailed comparison of the wall performance in terms of overtopping and scour, where numerical model could not. The model also provided precise wave load estimates and taking into account loads in the impulsive regimes. However, analytical and numerical models were found essential in the preparation phase, either to set the model condition or to select the measuring instruments. Some other numerical models were used to provide further insight in some areas where measuring was difficult on the physical model. And of course, other well-calibrated models could be used to test other hydrodynamic conditions and therefore save time and money for the project. This is the end of the presentation. Thank you everyone, and I remain available for any questions.